Hello and welcome, 8th graders. This is Mr. Callen coming to you, joining up with Miss Morris to help you with our e-learning activities for Wednesday, September 22nd. Hey, if you've made it this far, then you're already to the online agenda. And you're already clicked on the watch video here. So you may also choose to open up this worksheet. More on that in a second. Hey, don't forget our office hours. We are available. We have scheduled time in between our meetings. We've scheduled time to help you. 9:45 to 10:45. Send us an email, message us with Google Chat, or use your Gmail messaging service. You can get to us. We can do everything from talking you through a problem, checking some answers, even doing a one-on-one meet with some of you. So if you need us, let us know. That's what we're here to help. All right. If I could point out, please, if you click on where it says complete worksheet, click here. Some of you already have a paper document. None of Mr. Callen's students do. Most of Miss Morris' students already got the paper, but you are welcome to always use Kami to complete said assignments. And so if I click here, you'll see a screen that looks like this most likely pop up. I'm going to click open with Kami. You're also welcome to download it and then open it with Kami yourself, but I'm going to click open with Kami. Now at this point, it knows that I, Mr. Callen, own the document. But if you were to sit here and come to start trying to write on this, a big pop-up screen might say, wait a second, this is not your document. Do you want to make a copy for yourself? Blah, blah, blah. You know how they say it. In which case you would say something like, you would select the option that says yes, or make a copy. And then it would make a copy for you. I'm going to go ahead and delete that stuff so it doesn't appear on you guys' documents. And we'll carry into the lesson. Our focus, ladies and gents, after looking at our mid-tests, we have a weakness in computing scientific notation and just scientific notation in general. We noticed it after our quiz, got a little better with the mid-test, but we're still seeing weaknesses with scientific notation. Now remember, we first learned how to write big old numbers, or for that matter, very, 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 very small numbers. We learned how to write that in scientific. We then used that skill to compute numbers, whether it be add or maybe it's a subtract. I kind of like multiply. It's one of the easier ones for me. Perhaps it even says divide. That's our goal for today, is to review those concepts to really get our thinking straight before the post-test, which is coming up on Friday. Now, here we have the assignment that you have, but as you can guess, your teacher is not going to do your assignment for you. So I tell you what, every problem, I'm going to do a problem that looks very similar to it. As you're completing the problems with me for notes, look at the problem that I'm going to do, look at the problem you're going to do, decide for yourself how these problems are similar, how they're different. So let me just make up something with number one. I'm going to just say, let's about 905. Let's do 905 million, shall we? No, let's make it even bigger. Let's make it humongous. Now remember, when writing numbers in scientific notation, we are multiplying some number times some power of 10. I could copy these digits, but there's a special rule for that number. That number, I'm going to call it n, can be any number smaller than 10 and greater than or equal to 1. I often say between 1 and 10, but that could also include 1 exactly. Now, little disappearing ink here. Where could that decimal go to make a number between 1 and 10? Now, as you can see, 905 too big, even 90 too big, 0.905 too small. In fact, ladies and gents, there's only one place that decimal could go, and that is going to be in between the 9 and the 0. Now we have a number between 1 and 10. But please, please, please don't tell me yet that these two amounts are equal. How could $905 billion be the same as $9.05? That doesn't make any sense, does it? But if we multiply that 905 times 10 over and over and over again, then we can get back to where we want to be. We're placing the decimal here, but here's home base. Let's count. 1 and 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. The question then Is it 10 to the positive 11 or is it 10 to the negative 11? Now, I keep having students debate about, well, if it's going to the right, if it's going to the left, blah, blah, blah. I say debate because there tends to be a disagreement. See, some people start and go that way, while other people start and go to the left. So in this case, please don't look at, is the decimal that you're moving going to the right or the left? Instead, I would always encourage you, is this number huge, like multiplying by 10 repeatedly, or is it tiny? Remember, this is a nonsense statement. We switch it to its reciprocal, and the negative exponent becomes positive. This is literally 100 billionth. Well, if you look at that number, that's not tiny. It's huge, and therefore the exponent should be a positive 11. So make sure when you're thinking positive exponent, negative exponent, ask yourself, is it huge or tiny? Last thing I'll say with number one, with my example, is that if someone asked you, would you rather have the top amount of money or the bottom amount of money, what would you say? Now, I hope at this point you say, dude, Mr. Callen, come on. That's the same amount of money. It's just two different ways of writing it. Now, you have two choices right now. You can pause the video and go do number one and come back when you're ready, or you can continue on with the video as I do another example. Let's do an example kind of like number two. I'm just going to make this up, all right? So you got a lot of zeros. I'm going to put a lot of zeros. Let's see, you got a 329. I'm going to put a 6-4. Okay, so not exactly the same, but you can see that they are similar. Remember that we need to change this number into some decimal times some power of 10 in order that these two quantities are the same. They're exactly the same amount, just two different ways of representing them. Now, if we put a 6 and a 4 here, you're thinking to yourself, okay, can you put the decimal at? No. 64, that is not between 1 and 10. What about in front? No. 0.64 is smaller than 1. That doesn't work. In fact, there's only one place we can put the decimal if we're going to make this number in scientific notation. Now, 6.4, now there is a number between 1 and 10. But if this is where we want it, and this is home base where it belongs, let's go ahead and count the number of times that we have to change that place value. 1 time and 2, 3 and 4, 5, 6, and 7. Oh, wait a second. Should that be a positive 7 or a negative 7? Wait a second. This is a tiny, tiny number, and therefore the exponent should be negative. Literally, what this means is 1 10,000,000th of a dollar. So that explains why the exponent should be negative. Now, again, if you wish, pause, do number two, do number three. Come on back when you're ready to move on. Onward we go. Whereas the first three problems start with standard form and ask us to write it in scientific form, problems 4, 5, and 6 start with scientific and ask us to write it in standard. So allow me, if you would, please. Here we go. I'm going to make up a different one. You got 5. I'll take a 3. You got 0.81. I'll just make it, I don't know, 0.94. Sure. Times 10. Here you got a negative 6. I'll do mine negative 5. Now, I ask myself, if we have a negative exponent, is that huge or tiny? Oh, come on. That is a tiny amount. That's 100,000th of a dollar. Therefore, when I move this decimal point, I'm going to move it to make a tiny number. In other words, I'm going to move it in a certain direction 5 times. I'm going to fill in all the gaps. Notice that is not 5 zeros, is it? This is 0.000394. If you want to put, I would highly recommend putting that 0 in front. By the way, little disappearing ink here. Think about place value. We have the tenths. We have the hundreds. We have the 1,000ths. We have the 10,000ths. And look at here. We have the 100,000ths, which is, after all, what we said. All right. So I did an example. Those two quantities exactly the same. There's just different ways of representing them. If you wish, pause, complete number 4. Come back for number 5 when you're ready. For the rest of us, let's carry on. So you got 7.4. I'll make, how about 5.2? And you got 10 to the 8th. I'm going to do 10 to the 10th. Let's make it big. Speaking of big, 10 to the positive 10th power. Imagine multiplying by 10 10 times. Yeah, that's huge. So when we move this decimal point, let's move it in a way to make a huge number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here's where the decimal really belongs. And let's rewrite our answer. Now notice 1, 2, 3, 4, 5, 6, 7, 8. There are only 9 zeros, aren't there? Your choice whether or not you put the final decimal place. But if somebody said, hey, which amount of money would you like? 5.2 times 10 to the 10th or 52 billion? You're going to say, come on, man, that's the same amount of money. It's just two different ways of representing it. All right, finish up the front page, pause the video, come on back when you're ready for help on the back side. Second page, ladies and gents, is going to be a bit more of a challenge, and that's where we are going to compute numbers in scientific notation. As you can imagine, I'm not going to sit here and do your homework for you, so let me bounce. I think number 7 and number 8, sure, there's differences. The obvious difference is we're comparing subtraction to addition. I think, though, that the same tact, the same method would work. So let me do a subtraction equation. So you got 1.01. Let me make 1.03. You got times 10 to the 6th. I'll do times 10 to the 7th. And then you're subtracting 9.85, so let me do something 9.92. You got 10 to the 5th, so I'll make it 10 to the 6th. Now again, you see a lot of similarities in these two problems. There are clearly differences. How are we going to work this out? Most of us will do what I call the old school or standard way of doing it, where we're going to take each of these numbers, little disappearing ink here, and I'm going to change it to standard form. 1, 2, 3, 4, 5, 6, and 7. After all, 10 to the 7th, quite a big number. And let's do the same thing with the 9.92 times 10 to the 6th. Still a big number. Not quite as big. You can tell when you're comparing the 7 to the 6. So let's go ahead here. All right. Now take it from here, ladies and gents. All you got to do is subtract. Of course, you cannot take away 2 when you have nothing to take away, so we're going to regroup. 10 minus 2 is 8. Regroup again. 12 minus 9 is 3. And 9 minus 9, oh, there's nothing over there. Huh, interesting. So in this case, we're going to take one more step. Turn it back to scientific notation. Where's where we want the decimal place, but here's where it belongs. So we can go 1 and 2, 3, 4, and 5. Because it's a huge number, that should be a positive. Now, some of you, and a very few of you, will attempt this problem by leaving it in scientific notation. But here's the issue. You cannot subtract the 1 and the 9 because they're not in the same place value. And we're going to see if Mr. Callan made a mistake, because if we're doing it right, we should have the same answers. How about we change them to make sure they're both in the 10 millions place? But if we want it to go from 6 to 7, think about how that changes the decimal as well. So 1, 2, 3, 4, 5, 6. But we want it to be 7 places, so we need an extra place value. In other words, we're going to rewrite this as part of a $10 million bill. Now the reason it works is because here we have one $10 million bill, and we're going to take away a part of a $10 million bill. Now we can actually line it up and subtract. All right, still got to regroup. This is looking kind of familiar, isn't it? 12 take away 9. Sorry, that's a little bit messy with that 12. 12 take away 9 is 3. 9 take away 9 is 0. And we have 0. Whoa, how's this for weird? Now I have to pause and say, wait a second, that's not in scientific notation. We need a number between 1 and 10. But of course, if the 3.8 changes, now think about this. Instead of going 1, 2, 3, 4, 5, 6, 7, got a little marker happy there. Now we don't need to go this way and we don't need to go this way. In other words, it's 2 less place values. Well, would you look at that? Same answer. 2 different ways to do it. Again, only select students have Miss Morris and Mr. Callen's permission to be doing that. Most everybody else, change it to old school standard form. Go ahead with the addition or the subtraction. In this case, it's a subtraction problem. And finally, change your answer back into scientific notation. You may pause and come on back when you're ready. Last but not least, ladies and gents, multiplication or division? Multiplication or division? Let's go with multiplication. Division is very similar. So not going to sit here and do your problem for you. You got 5.9. How about I do 4.6? You got 10 to the 9th. I'm going to do 10. I'm just going to go easy here. I'm going to do 10 to the 4th. Multiplication symbol, you have 2.18. Let me do 3.11. 10 to the 7th, I got 10 to the 6th. All right, now how do we do this? If I do this example, you guys should be able to handle number 9. First thing we remember is that with multiplication, we can change the order and still have the same answer. Think about it. 1 times 2 times 3 is the same as 1 times 3 times 2, which is the same as 2 times 3 times 1. So multiplication and addition is commutative. We can change the order and still have the same answer, and let's do that. Let's change the order, put the decimals next to each other, and then the powers of 10 will be next to each other. Come off to the side, I'm going to multiply 3.11 times 4.6. Remember, when multiplying, you do not need to line up the decimals. 6 times 1, 6 times 1, 6 times 3. Now I put an X, some of you put a 0 to mark off that place value. 4 times 1, 4 times 1, 4 times 3. Add it up, 6 plus nothing, 6 plus 4 is 10, so we carry the 1. 1, 8, and 4 make 13, carry another 1. 1, 1, and 2, and 1. With, count it, 1, 2, 3 decimal places. So we multiply these decimals, we're going to get 14.306. Now, I like to put little ones underneath here. You don't have to. Just asking myself, is this making sense or is it nonsense? Well, 10 to the 4th makes sense. We know what that means. And 10 to the 6th makes sense. We know what that means. Is this a combine or a cancel? Sure looks like all those 10s will combine. If we had 4 of them and then we have another 6 of them, that means we're going to multiply by 10 to the 10th power. Stop, freeze, time out. Remember, we always have to ask ourselves, is that answer in scientific notation? And when I look at this, I am seeing a number that is not between 1 and 10. So we're going to have to rewrite this with one more step. Changing our decimal place, now we got a number between 1 and 10. But how does that change the power? So instead of going 10 places, 2, 3, 4, 5, 6, 7, 8, 9, 10, we want it to be right here. That's an extra place. So our final answer for our example is 1.4306 times 10 to the 11th. Now look at how that problem is similar to number 9. Look at how it's different. Look at how it's similar to number 10. Multiplication and division, you can simply divide the decimals and divide the powers of 10. All right, folks, that's what we got. This video is long enough. Go ahead and take care of the rest of your assignment. 10 problems for the day. Take care, bring some questions, and let's grow.